Okay, good morning, everyone. Last topic of chapter 2, we will look at source transformation and maximum power transfer theorem. Shouldn't take longer than 5 to 7 minutes. And then we'll begin chapter 3, which is inductors and capacitors. Okay, does anyone have any questions before I begin? Okay, all right. So we went over the concept of Thevenin and Norton equivalent circuits and stated that we can describe a large linear circuit with multiple sources and multiple components as a single voltage source or a single current source, right? So if A equals X and B equals X, we can state that A equals B. And source transformation concept comes from that. That both of these circuits, the Thevenin and Norton circuits, are equivalent circuits of a single large circuit, and so they are equivalent to each other. So if you have a voltage source in a circuit, you can transform it into a current source and vice versa, back and forth. And in some cases, it is useful technique. So we'll go over an example after this. But the thing to keep in mind is that the Thevenin circuit is a voltage source in series with the resistor, and the current source is in parallel with that resistor. Okay. So certain conditions have to be met in order to apply source transformation. I'll be frank with you, it's not one of my favorite techniques, because I tried to do this sometimes in some circuits, and I ended up getting the wrong answers. Yes?
So technically, we move on to this question, we probably never use this.
Not necessarily. So the question being asked is, would we ever be able to use this? The answer is yes, you would come across situations where you would need to use this. That is the purpose of why I'm actually teaching. So it's a technique that would simplify your circuit. It's in some cases, not all of them, but some cases your circuit can be simplified to a large extent. Of course, the equation that relates the two is Ohm's law. So if you're transforming back and forth, the values that you obtain is from Ohm's law. Thevenin voltage is the product of Norton current and the Thevenin resistance. All right. So let's look at this example. If you look at this example on the left, you see two sources and two resistors, right? Normally, if you see more than one source, if you see two sources or three sources, you would think you would have to perform nodal analysis or like node voltage analysis or mesh current analysis or superposition, right? That's the first thought that comes into mind. But if you look at the circuit, obviously this particular example has voltage source in series with a resistor and the current source in parallel with the resistor. We can take this source and transform it into a current source, or we can take this current source and transform it into a voltage source. So circuit B is where you transform this into a voltage source, and C is where the voltage source is transformed into a current source. And then your analysis becomes very simple. Okay, now you simply have two voltage sources in a circuit, or you have two current sources in the circuit. You can simply apply Ohm's law and solve the entire circuit. Apply KCL, KVL, and solve it. So instead of performing multiple steps of node voltage analysis and writing out equations, or mesh current analysis or superposition, it is now a 2 or 3 step answer. Okay, so let's see how this will work. What we would do is we would break up the circuit right here in the middle. You have to break it up at the point where the voltage source and the resistor is connected. Okay, so if I break up the circuit, it would look like this. I would have a voltage source I would have a series resistor. I would mark those nodes in the original circuit, A and B. The reason is that after you perform your transformation, the current source should go back between those two nodes. If it does not go between those two nodes, your circuit would end up incorrect. And this is one of the reasons I do not prefer this, or I tell students you have to be very, very careful, because taking it out of the circuit and plugging it back into the circuit, that requires some practice. And so if you draw the other side of the circuit, it should look like this. Again, the nodes remain the same, of course. This is R1, 5 ohms. This is the 20 volt source. This is the 1 amp current source. And this is R2, 10 ohms. Now, if I transform the right side between nodes A and B, the resistor, of course, remains the same. So the current source is now changed to a voltage source in series with that same resistor. So source transformation would work by applying Ohm's law. Here I'm given the current 1 amp. I'm given the resistance 10 ohms. So my voltage source is V equals IR. 10 times 1 gives me 10 volts. Resistor value remains the same, R2. And then you plug this transform source back into the original circuit. When you do that, you obtain the circuit that is shown in figure number 2 or figure B. All right, write it down, take a pause. Let me know if you have questions. Any questions?
Professor?
So now, if you look at circuit number B, you can simply apply Ohm's law and determine what the current is flowing through that entire circuit. That's it. You can apply KVL. You apply KVL, you can find the voltages across those resistors, determine the current through there. Right? This R1 and R2 are now in series. You can combine those resistances and you apply KVL around the loop. You can find the voltage across those two resistors. Once you have the voltage across those two resistors, you can find the current by applying Ohm's law, and you can solve for any other quantity in the circuit.
Professor?
That is the advantage. Yes, go ahead.
Why when you convert it to a volt source, do the resistors go into series? When you convert it to a current source, they go into a parallel.
So representation, so that's a good question. So the representation of a voltage source is always in series. So I think it goes back to chapter 1. When you model a real life or a ideal voltage source, if you put a resistor in parallel with a voltage source, what is the voltage across that resistor? It's the same as the value of the voltage source, Vs. Okay. Now, in real life, some amount of the voltage supplied by a voltage source is consumed inside the voltage source itself. So the question is, how do we represent that power consumption? Yes. Yes, but that's a separate question. I'll come to that. Okay, let me finish this explanation though. So again, as I was saying, so we have to represent the internal resistance of the voltage source that will consume some of the voltage itself. Now, real life voltage sources are designed with that consideration in mind. So if you set a voltage source to output 10 volts, internally, the circuit is built up in such a way that the internal resistance should be as small as possible. But again, it can never actually be zero. So we define that internal resistance of the voltage source as being in series with that voltage source. If we represent it as in parallel, we cannot accurately describe a voltage source at all, because the voltage source would be in parallel with the resistor. The voltage remains constant across the resistor, and then it would not describe that voltage source accurately. Does that answer your question?
Yes, it does. Thank you.
And the same thing happens with a current source. So if you have a current source will supply its rated current irrespective of what is connected at the output, similar to the voltage source. If you connect it in parallel, if you connect it in series, it does not matter what the resistance is, right? Could be infinite resistance. By technical definition of the current source, it will supply. If it's supplying 1 amp, it will supply 1 amp to a 1 ohm source, 1 ohm resistor, or a 1 mega ohm resistor. So we cannot accurately describe the internal resistance of a current source with the resistor in series. Hence, we put it in parallel. And parallel would show that the current coming out of the current source, some of it might be consumed inside that current source itself.
Thank you.
Okay, so as I was saying here, circuit B can be solved using KVL, Ohm's law, etc. Simple techniques versus nodal analysis or mesh current analysis. So your question was, you remind me again? C. Okay. Yes, so I'll go over that right now. The question being asked was about figure number C. And so I would take the voltage source. Actually, I'll draw it out right here. And I would transform it into a current source in parallel with that same resistor. A, B. That resistor, of course, still remains R1, 5 ohms. And from Ohm's law, I get the value of the current source as 20 divided by 5, so 4 amps. And then you plug it back into the circuit, you get figure number C. Now you have both sources going in. You could solve C using KCL and Ohm's law. Both currents are coming in, meaning they add up. If they add up, you have the total current going into those two resistors. You can apply current division, or you can find the voltage across those resistors by applying Ohm's law and solve for any other quantities. Does that make sense? Right. Any questions?
I have a question.
Sure.
So when you're solving these with KVL or Ohm's law, are you solving them like separately of each other, or
No, we
like
simply apply, let's say, for example, in circuit B, if you apply KVL around the loop, we can see it's 20 in opposition to 10. So it'd be 20
Right.
minus 10. And then we can find voltage across both the resistors. So
Right.
R1 plus R2 was give us a single resistor. And so the resulting voltage would be 10 volts applied across 15 ohm resistor.
Okay, cool. Thank you.
Yeah. All right. Any other questions? Okay. Maximum power transfer theorem states that in order for two circuits to transfer power or maximum power to be transferred from circuit 1 to circuit 2, the Thevenin resistance of the first circuit and the second circuit should match up. Okay, so oftentimes in electronic devices and electronic circuits, you have a cascading connection of different circuits. One of the most common examples I like to use is audio video receivers. So if you have if you have an audio video receiver, it comprises of a preamplifier stage, right? So you have an audio video receiver. It has a preamplifier stage, more commonly known as a preamp, which then drives the amplifier or the amp, which is then connected to a speaker. So in order for maximum power to be transferred from one stage to the next, the succeeding, meaning the second circuit's resistance, should be the same as your Thevenin resistance of the first circuit. RL represents the load, right? So RL represents the load resistance or the second succeeding circuit. The succeeding circuit, and the resistance of the second circuit or the succeeding circuit should match up to the Thevenin resistance of the preceding circuit. So RL should be equal to RTH. RL should equal RTH. That's what the maximum power transfer theorem is. The maximum power transferred, and again, there's a derivation that we do to determine this equation, is given by PL max is voltage square divided by 4 times RTH. Okay, it simply is given by summing up RT and RL and then applying for the voltage across RL. Voltage power equation, if you remember, is V square over R. V square over R. So if RL is equal to RTH, it is 2 times RL or 2 times RTH. Okay, that's in a nutshell, that's what maximum power transfer theorem is. Now, maximum power does not mean maximum efficiency. Okay, maximum efficiency is not achieved when you're trying to deliver maximum power. So it depends on your use case. So the use case scenario of when you want to transfer maximum power and when you want maximum efficiency. So different scenarios and different applications require different circuit design. All right, any questions? So students who are taking the lab, this is the lab for next week. How many of you have, there was a comment on the feedback, was that their labs were ahead. So some students have, there were several students who are in those labs. Anyway, I'll address that once everyone finishes writing it down. Does anyone have any questions about maximum power? Yes. Saying V, this? Oh, B, yeah, that's basically you have the circuit, and the circuit is represented as a Thevenin equivalent network. That's what it is. Sorry, I should have explained that. Yes. So it's a large network. So it could be that square box could be a preamplifier, could be an amplifier, and it's driving a load. So depending on what is connected to the output, that output is the load. So it could represent any circuit. Again, taking that example one step further, if you look at the speaker specs for any speaker, tiny drivers, headphones, earphones, big tall boxes, if you look at the specifications, the speaker will always have a specification of impedance or resistance, if you will. And that will state it's either 4 ohms or 6 ohms or 8 ohms. Most of the big ones are 8 ohms. Headphones, at least the older drivers, used to be 32 ohms. Those are used to match the output of the amplifier. Most amplifier outputs are 8 ohms. So if you look at the specification for a amplifier, you can download the PDFs from online, any website, any manufacturer. On the last page on the specifications will tell you it can drive a 8 ohm speaker with like 100 watts. So that's what it's trying to do. It's trying to match the resistances of both at the same time. Yes. Yes, you can. Yeah. If you're dealing with current sources, yes. It wouldn't be divided by exact. You'd have to derive it and then do the equation, because for current, P is equal to I squared times R. For voltage, it's V squared divided by R. So the equation would be different, but the principle is the same. Question being asked was, can we use a current source or Norton equivalent and do it? And the answer is yes, we can. Okay. So as I was saying, this is the lab for next week, right? So the course is on schedule, but every quarter it happens, unfortunately, that there is a Monday holiday. So the labs that are on a Monday or a Tuesday lose 1 class, right? There's a holiday coming up at the end of May. Memorial Day, I believe. So that following Tuesday is going to be a Monday schedule. So Monday loses a class in this quarter, and Tuesday also loses 1 class in this quarter. And so because of that, some instructors jump a week ahead and start from the first week of classes, which kind of messes up the synchronization between the lab and the lecture. To compound that, to make matters worse, is if it's later in the week, if the lab is later in the week, like Wednesday, Thursday, Friday, then we still have time to catch up. But this is like, we are not only 1 week ahead, the lab is not only 1 week ahead, but it's very early on in the week. So trying to get that material done in the class itself is virtually impossible. And that's the explanation for that. But because of that, the lab write-ups are very detailed. Everything a student needs to learn about the lab theory is in the lab write-up. All the equations are also stated in the lab write-up. So reach out to your lab instructors, reach out to me. I'd be more than happy to, help out students. But it would not be possible to cover everything in class. We just would not have enough time to go through everything. But read through the lab write-up and then approach your instructors with the questions. That's what I would say. Okay. All right. So that's the end of chapter 2. Let's go on to chapter 3. Capacitors and inductors. Now, you have students do a bit of inductors and capacitors in the physics classes, right? I think some students previously told me they did something in high school also. But again, regardless of high school, the pre-req classes do cover capacitors and inductors. What we'll do here is we'll look at the equations. We'll look at basic theory governing inductors and capacitors, the phenomenon of inductance and capacitance. We'll see how the voltage and current and power is associated with the inductors and capacitors. So that's for chapter 3. And in chapter 4, again, we will study inductors and capacitors, but it'll be a small portion of the analysis. And when I say small portion, I do not mean the chapter is small. I mean, actually, let me back up. Inductors and capacitors are different from resistors. They are energy storage devices. Okay, they're energy storage devices. They do not have any energy of their own, but they can receive the energy and release the energy back into the circuit at a later point in time. That energy transfer does not take place instantaneously. Okay, it does not take place instantaneously. It takes a while for the energy to be acquired, and it takes a while for the energy to be released back. So in chapter 4, we will look at the energy transfer phase. Okay, we look at the energy transfer phase of that entire process. And when I said small, I said it's small because the energy transfer could take place in milliseconds. It could take place in microseconds, depending on the size of the inductor and capacitor and depending on how much energy you're sending. So the analogy I like to use is think of it as a bucket of water that you're trying to fill. If it's a small cup, few drops or a few spoons of water would be enough to fill up that small cup, right? If it's a large bucket, depending on the flow of water, depending on the flow of fluid, depending on the size of the tap and the size of the pipe that's bringing that water, it might take long, it might take short time to fill it up. And that's exactly what the capacitor inductor is, okay? Depending on the energy source that is sending, whether it's a voltage source or current source, depending on the size of the voltage and current that's being sent to the capacitor or inductor, and depending on the pipe, basically the resistor that is connected in front of the inductor and capacitor, it might take long, it might take a short while. Typically in electric circuits, capacitors and inductors are very, very small in size, sometimes in the order of like picofarads or femtofarads. So the energy transfer we are talking about is in like microseconds or nanoseconds, very, very quick. So in chapter 3, we will look at the larger picture where we look at all the equations about voltage, current, and power that govern the voltage, that govern the quantities for the inductors and capacitors. And in chapter 4, we'll look only at the charging and the discharging phase. So again, when I said small, I'm just talking about the charging and discharging phase of energy transfer. Okay, so chapter 3 will introduce inductors and capacitors. So inductors store energy in the form of a magnetic field. So the energy associated with inductor is associated with the magnetic field. Energy associated with the capacitor is associated with the electric field, the electrostatic field. And we will not go too deep into the physics of things. We'll stay on the engineering side of things, okay? But I will go over some of the basics, right? Magnetism is an important part of everyday life. Nearly every single electronic device or every single electronic component that we use today uses or employs electromagnetism, okay? As a real life example, if you have a phone with a wireless charger, like you put your phone down the back, so the back of the charger is a coil. A coil is nothing but an inductor, okay? When you place it down on the wireless charger, the charging plate also has a coil. You bring those two coils together, now you have a phenomenon that is known as mutual inductance. And so energy is transferred wirelessly from one coil to the other coil. So again, common examples, generators, motors, transformers, the basic foundation blocks of electricity and electricity distribution as we know it, okay? And lots of researchers did a lot of research into electromagnetism. The most famous ones are listed here. Ampere was one of the first ones to come up with what is known as the Ampere circuital law, right? In the early 1800s. And then based on that work and the work of several other researchers, prominent names in the field are Michael Faraday, Carl Gauss, James Maxwell. All of these names you may have heard of before. Many of them have quantities and units named after them, okay? But again, as with anything, there are several other people, like hundreds of other people and researchers around the world who contributed. These are just the ones that, published and became famous. Okay. A wire inherently has resistance, capacitance, and inductance, okay? The resistance, inductance, and capacitance is very, very small, and also it does not rise to the level of interference for its stated purpose. So if I pick up this HDMI cable here, or if I pick up this power cable, it has resistance, it has inductance, and it has capacitance. But again, the resistance does not rise to the level of interference. Its job is to carry 120 volts from the power outlet to the adapter. So 6 feet long, resistance is there, it's very small. Maybe it's measurable, maybe it's not. But the level of the resistance will not interfere with its job of supplying 120 volts. Similarly, it has inductance, it also has capacitance, but the level does not rise to the level of interference. So anytime you have a wire, a current carrying conductor and current passes through it, a magnetic field develops around that conductor. That field is very, very small, very, very tiny, very small. And we have what are known as the magnetic flux lines. Okay, that's the direction of the magnetic field. You can use the right-hand rule. Where did it go? Actually, take it out. You can use the right-hand rule. And this is, again, if you wish to learn more about the physics of things, to actually illustrate the current carrying conductor and the direction of the magnetic flux lines. So if you use your right hand, your thumb pointed out, then the thumb points towards the direction of the current, and the magnetic flux lines, the fingers. Okay. So if you have any wire and you're sending a signal out, meaning if I plug a cable into the wall and I wish to find the direction of the magnetic flux lines, you would simply point it in direction of the power out, away from the power outlet. And then it would tell you the direction of the magnetic flux lines. Again, the magnetic field is very, very weak. It's not strong. If you take that same cable, if you take that same wire and you convert it into a spiral, sorry, a loop, a single loop, then the magnetic flux lines get aligned and it points outward of that loop. Okay. So it's going into that loop and out in this direction. Okay. All of them align in that same direction. If you create multiple loops using that same conductor, same wire, now that magnetic field gets a little bit stronger. Okay, magnetic field gets a little bit stronger. The physical shape of that coil aligns the magnetic flux lines to form a sort of a magnetic field. The magnetic field has a north pole and a south pole that moves through the center of that coil. Okay. It's a complete circle. The flux lines are complete circles, so it does not have a beginning. It does not have an end. It does have direction, though. The point of exit is pointing towards north. And then other researchers found that if you inserted a magnetic material to the center of that coil, that magnetic field now has something to grab onto, and it becomes even stronger. Okay. A magnetic material is a material that has the capability to induce magnetic flux lines with ease. Okay, so if there's a material through which the magnetic flux lines can be established very easily, that material is known as magnetic. Okay, stated as magnetic. This is also the working principle of a electromagnet. Right, electromagnets. You can make strong electromagnets that are similar to permanent magnets by employing and applying a current flowing through a conductor. If you have a magnetic core inside that conductor, you can create a very strong electromagnet that can actually pick up heavy vehicles by itself. Perhaps you might have seen pictures or videos of vehicle junkyards where you have these cranes that'll pick up vehicles employing an electromagnet. It's a beautiful design because you flip on a switch, now picks it up, and you turn it off, you can drop it off. Okay, so from there, we establish the principle of inductance. So a current through a coil establishes a magnetic field. That component that is wound as a coil is referred to as an inductor, and the phenomenon is known as inductance. Okay, inductor is symbolized by the notation L, uppercase L. Okay, uppercase L. And the unit is named after anyone? Joseph Henry. So Henry's. It's noted by uppercase H. I should have said it was named after me, but that's not really true. So I'm assuming you have covered at least these basics in physics. Inductors, L, Okay. All right. So uppercase L stands for an inductor. Uppercase H stands for Henry or Henries. And that's the unit of inductance. And again, like resistor, inductors and capacitors are passive components. Okay, they cannot create any energy of their own. They can only accept energy, store it, and then release it back into the circuit at a later point in time. Okay. The energy is, of course, associated with, students still writing it down, okay, associated with a magnetic field. Capacitors, as we will see later, is an electric field or electrostatic field. And again, repeating the passive component thing, resistors, capacitors, inductors are all passive components. So they follow the passive reference configuration or the passive sign convention. Point of entry is always plus, point of exit is minus. Current always flows from high to low. So for resistors, capacitors, and inductors, current will always go from plus to minus. Okay, same as a resistor. Okay. Physical construction of an inductor is governed by this equation. Inductor value L is given by mu n square A over L. That L is the lowercase l. It stands for length. Okay, this is not one, this is length. Length of the inductor coil. Okay. So it's a spiral coil made out of some metal. And every turn or every loop is counted as a turn. It's a spiral coil. It will have a number of turns. That number of turns is stated by N. And mu is the permeability, and that is given by mu0 times mu r. Mu0 is the absolute permeability. Mu r is the relative permeability of the core. Okay, relative permeability of the core. In this image, in this illustration, there is no core. It is simply air. So we call it as an air core inductor. Relative permeability of air is just 1. Okay. Mu0 is a constant. Actually, I had the number somewhere. Let's see. 4 pi into 10 raised to minus 7 minus 17, the constant. I'll find it and post it. Let's see. All right, any questions so far? Anyone? Okay. All right, so as I was saying, mu is the permeability. It basically is describing the ease with which magnetic flux lines can be established inside a core material. If there is no core material, then that material is simply air. Okay. And mu is the product of mu0 times mu r. Mu0 is the absolute permeability. Mu r is the relative permeability compared with the absolute permeability. Mu0 is a constant. I believe it's 4 pi into 10 raised to minus 7 or 17. Okay. Now, theoretical analysis, we state that the inductors, resistors, and capacitors are all ideal, right? They're all ideal. So if they're ideal, then the value that is stated is absolute. If it says 10 millihenry inductor, it is 10 millihenries. But in real life, obviously, if you're doing the lab, you've seen that. Obviously, we cannot have an ideal component, right? So for an inductor, which is made out of a coil of wire, that wire will have resistance. Okay. If you take this inductor and you measure the resistance from one end to the other end, you will measure some resistance. That resistance is part of the coil itself. You cannot separate it out. Make sense? Right? It's a coil of wire. If you measure the inductance, it'll give you a value for the inductance. If you measure the resistance, it's going to give you the value for the resistance also. But it's physically, it's the exact same coil. You cannot separate it out. Okay. So a real life inductor can be modeled as an actual inductor in series with that resistor. And this box comprises that inductor. Okay. So let me just point it out. This inductor will be labeled as L, and this would be labeled as RL, inductor resistance. It is part of the inductor. You cannot separate it out. Okay. This information is going to be useful in lab number 6. Okay. L and RL. And this is also the reason why a real life inductor cannot hold its charge indefinitely, because it will discharge through this resistance. Let's say you charge an inductor with a large amount of energy, and you leave it alone, right? You disconnect it from the circuit, you leave it alone. What do you expect to happen? You would expect, if it's an ideal inductor, that the energy will be stored in there for an infinite period of time, right? But in real life, that energy would be dissipated through that internal resistance as heat. All right, let's take a pause, think over that. Let me know if you have any questions. How are we doing on time? 9:53. Any questions? Rob? Okay. So just some examples of real life inductors. These look like resistors. They have some bands on it, or it's written up. Yes. Some of them might have coatings, yes. That is a possibility, but there's no insulation on top. There is no insulation. Path of least resistance would still be through that wire itself. Yeah. So as an example, if you take a look at the first one and the second one, thick wire, right? Thick wire, so lower resistance, very few turns. In B, high number of turns with a thinner wire. So if you look at those resistances, 6 milliohms, meaning 0.006. This is 0.4. Okay, 100 times difference. if you look at the equation, sorry, here, inductance is directly proportional to the square of the number of turns. Here, inductance value is 1 millihenry. Here it's 10 microhenry. 1 millihenry is about 1,000, right? 1,000 microhenries. So again, 100 times higher inductance value with a thinner wire, but a large number of turns that establishes a large magnetic field. Okay. When it comes to current carrying capacity, again, physical material makes a difference, right? Thicker wire can carry large amounts of current, thinner wire can carry lower amounts of current. So I particularly like to point out these two examples as the difference is 10 amps, 1.3 amps. Okay. So real life examples of how different inductors can be created using different number of turns, different physical attributes. All right. The inductor equations that govern the quantities are listed here. Voltage V is given by L di over dt. So now we look into equations, the quantities for inductors and capacitors that are time dependent. Remember, I said energy transfer takes place, but the energy transfer cannot take place instantaneously. So everything is now dependent on time. Okay, it's a time dependent quantity. So voltage equation, this is the primary VI equation for an inductor. And mathematically, when we talk about inductors, we always talk about input as a current. So we talk about current input and voltage as an output. Okay, so if current flows through an inductor, it establishes a magnetic field and voltage appears across that inductance or that inductor. V is L di over dt. You reverse it, meaning you want to find the current, you perform the opposite of differentiation, which is integration. And you integrate, you take L on the outside, on the other side, you get 1 over L integration of V. Okay, 1 over L integration of V. Now, integration is nothing but summing up of individual slices, right? dt is the individual slice, and then you sum it all up from period given from t0 to t. When it says t0, t0 is simply the time at which you begin analysis. Actually, wait. Actually, yeah, that choice of words is okay. Time at which we begin analysis. And then t is, of course, any variable time t where we end analysis. Sometimes we need to analyze for a certain portion of time, right? Circuit might be on for, let's say, 24 hours, but you only want to analyze, let's say, for a few minutes or a few seconds. Okay, so t0 would be 0, or it could have any other value between 0 and 24 hours. So it's basically the time at which we begin analysis does not mean it has a value of 0. It could have any other value. So you could break up a long period of time into multiple pieces. And if you're analyzing a piece in the middle, that will have a different value of t0. Does that make sense? Right? So t0 could be any number, could be any value. It's simply the time at which we begin analysis. And t is a variable, but again, it indicates the point in time where we end our analysis. Okay, so it's simply the beginning of analysis and the end of analysis. That's it. It will have any other value. All right, so let's end class here today. And I will pick up here again on Monday. Quiz on Monday based on Thevenin and Norton. We won't do, I mean, I'm not going to ask you to perform a complete analysis, but what I am interested in is to see how you're able to set up the problem correctly. Okay. And so basically I would ask you to actually look at multiple circuits and then draw the circuits that would be required to solve for Thevenin, Norton, and resistance. And I will post an announcement with the details. But again, quiz as usual on Mondays. Have a good weekend.